for the our fifth or sixth year in a row, we've been at the Coleman Pavilion presenting a story that's been pretty similar, but has actually grown. When we came here 6 years ago, we were known as developing the premier design tools in the semiconductor industry. The key for that, we're going to go over that a little bit, has always been the key. We're following the tenets of commercial companies, the commercial mantra of first-class success. We're going to talk about the reasons for that now too. But while we've been also presenting here, we've also been working with the Department of Defense over the past 9 years, working to implement these type of capabilities. And why are we trying to implement them? Well, frankly, why have we been so persistent in this area to talk about it? And it's simply because of this. Even though the technology that we're going to be talking about today, at least in electronics, was actually developed, funded in part by the Department of Defense, these are the types of payoffs they can realize. A 50% reduction of acquisition sustainment costs, a 50% reduction in operations sustainment costs, near 100% readiness rate, and agile modernization at the speed of relevance. So what's been the issue? The issue's been pretty simple. They look at this and they say, and you know how good our warfighters have been, and you know how hard our defense industrial has worked. They say it's too good to be true. It can't be the case, especially this 100% operational readiness rate. We've been challenging them lately. We say, well, you know, the average price of a new car is $70,000. You expect that to start every time, don't you? Well, yes. You expect everything to work on it every time, don't you? Well, yes. But then they'll say, but you have to operate a fleet of them. I said, okay, you got one, your wife got one, your kids have one. You expect all to work all the time, right? Yes. Well, if you expect it to work when you spend your own money, why do you make an exception when you're spending taxpayer dollars? And that's when it starts resonating. And so this is what is the pillars of commercial product development. Now we are, we support the NASDAQ Magnificent Seven, and this is what the commercials and now the DoD and the Ministries of Defense are actually demand from our tools. First, they have to develop a strong business case. They use our tools to say, this is why what we're developing is crazy great. This is why it's much better than the competition. This is how much time we know it will take. And this is how much money we think it's going to cost to make it. And this is how much we can sell it for. Just basic engineering case 101. But that's what they use our tools for. And they set benchmark product system requirements. They say this product has to have a lifespan of so much. So the requirements have to be here before the competition catches up. And what's really most important, in the commercial world, you can't build something, test it, and rebuild it. You build it once. Because you have this milestone, happens every year, it's called Christmas. You can never reschedule it, and missing it is fatal for most companies. The goal really is benchmark a high-quality, profitable product that delights the customer. And time to market, obviously, is key. These are some of the benefits you see. You know, I'm not going to, but it gets down to some of the basic tenets by the pioneer in the aerospace market, Kelly Johnson. If you can't do it with brain power, you can't do it with manpower overtime. You got to think about it first before you do it. Gensi Jujitsu is pretty simple. You go to the source to find the problem. I'm going to show, the next chart's going to show you about that, what I mean by that. And then always make your products customer friendly. Make it something that when you think about the person who spends most time with it. By the way, our friends who are in the depots, they love this one right there. So what's the mean by Gensi Jujitsu? Get to the source or the problem. Well, this was a chart that was actually in Forbes magazine 2024. When you have the attitude of, well, we buy boxes, we're integrators, but what's inside those boxes? 6,500 Chinese source semiconductors, and I don't mean People's Republic of China. I mean, I don't mean Taiwan. I mean People's Republic of China. This is what you see right there, and this really caught the attention of our friends in the Pentagon. And you can imagine what that does in terms of operational readiness rate. So there's a system out there called the Trusted Supplier Network out there by the Department of Defense. We work with them. They've got the full capability. We're the designers. We work with them to design stuff. We have trusted foundries, packaging, boards, all the way to enclosures that you can make trusted electronic systems using this trusted supplier network. This is the elephant in the room. And yesterday I had the honor of touring a lot of the flight line out there, looking at all these U.S. systems. And I saw the F-16, the F-15 out there, the Strike Eagle. It occurred to me that I was in third grade when that thing first flew. Last year at Farmer, we talked about the 50th anniversary of the F-16. That plane, I saw that fly when I was in seventh grade. We keep our stuff around for a long time, so sustainment and modernization is even more critical. And you think about it, how do we do in the electronic world? You get software upgrades, every other week, because you have to punch in your passcode into your phone because somebody found a glitch. They used that, and then they found a software patch, put it up there. That's what it is. And if you don't have the data packages, it really complicates it. We know that because of the number of customers that we talk to. So when we talk about this digital system, electronic, and you're hearing the word digital nowadays. Digital is the new sustainment, right? We don't talk sustainability anymore. We're talking about digital. Well, what does that mean? Well, it's a process that covers the entire life cycle. You're not addressing the development, you're addressing the back end too. It's a project management practice. We are now developing the tools that we have. When you can't miss Christmas, you don't stop a program for a project review. What is it? When you have a CDR, you basically stop the project for 6 weeks. You can't do that. It's real-time program management. It's a culture. Everybody thinks about when they're working on it. Okay, this is what it'll do for the product, but what else will it do? What is it backwards compatible? What's it going to do for the future? How much power? So you take all those, I'm old school, all those abilities, sustainability, durability, all that, you take that into account when you're doing the design. And it's a commercial best practice. And if you were to email me and ask me for a card, I will email this report to you for the Government Accountability Office, where they confirm that is indeed a practice, about how much testing and evaluation and design iterations commercial companies do before they actually build something. And that's what we call the shift left, look right facility capability, and that's used as hardware across digital twins. Well, one of the first arguments you hear from people is say, well, that's fine and dandy, but military systems are much more complicated than commercial systems. And that's really not true anymore. This is how many lines of code it takes to operate a Joint Strike Fighter. And you see how long it takes to go from concept to full operational capability. This is how much, for those of you Americans in the room, F-150 pickup truck, how much line software it takes to operate a F-150 pickup truck. And there's only one of those that has a bumper warranty and occasionally a rebate. So you say, well, but look what they did on the automotive, where they've actually shortened the time to market. And you look at how many electronics are in there. And you just look in 2010, we stopped right there. If you want to see what it's like in 2025, I'm going to show you. So I was in San Francisco a couple of weeks ago, and I called a taxi. I said, okay, here he is. He's going to go around the corner, pick me up. And there was no driver. We're at autonomous vehicles now, autonomy taxi systems. I think Waymo just had their millionth passenger. So this is where we are in the commercial. You think about it, you have to avoid product liability, right? It has to have 100% operational readiness rate, right? Because if it's not working, it's not making money, right? And you can imagine how many lines of software there. By the way, do not skip out on these guys, because if you skip out of it, this thing jumps out of the back of the car and chases you down. So anyway, so what are some of the, what's the issue in terms of adopting these type of best practices? Well, this is how currently the test and evaluation is done on electronic systems. You build a piece of hardware, and you test it as best as you can manually, and you test it just to see whether or not it meets the top level specs. And something that we found working in here now for 9 years is that, well, if you don't meet the test point, the performer doesn't meet it, they can write a waiver report. And if the government accepts the waiver report, they say, that's it. Isn't that something? And what? That's when you end up with these build, test, fix type cycles. And for the program office, they finally say, all right, screw it, we'll just live with it, we'll live with it, we'll fix it with a block upgrade. And then, by the way, for those of you who saw the 2018 defense strategy where they talked about where the SecDef Madison, no more block upgrades, design them like electronics, that's because when Mad Dog and I met, he got what we were trying to do right here. So this is what shift left, look right is. And it really is the ability to test and evaluate before you fabricate, to address sustainment issues while it's still in the design phase, and you're able to get early delivery of the designs to all the customers and all the stakeholders they're going to be impacted by that system. Other performers, like in case, like let's say this is like a sensor system for a weapon system. It's going to be going on there. Well, the weapon systems guys, as they get the design before it's built into hardware, they can test and say, is this really going to do what it's going to do? And if not, they can make suggestions on how to improve it. The software designers start designing the software on the system before they actually have hardware, such that when the hardware is ready to go, you've already verified the software with it. It all gets down to this concept called hardware accurate digital twin. And that's the first thing, that's another area we're finding just a little bit of translation needs to be done. After all, it's all about communication, right? So if you look at this chart, the only thing that's not digital engineering on this chart is this first one called document-based engineering. It's how I grew up. How many of you still have your drafting boards? I do, my T-squares, my drafting kits. That's document-based engineering. Then you get model-based engineering. And this is where we see a lot of the aerospace and Department of Defense world. Model-based systems engineering. There you go. That's a great first step. But what's the issue? This first word, model. It's a model. It's a representation of what you think is going to be built. We are at this stage where hardware accurate manufacturing correlated. What you have on the computer can go directly into a manufacturer, a manufacturer, and they build the exact thing, and you know it works. And that's why you're seeing a lot of when you see HADT, it's hardware accurate digital twin. This is where the Department of Defense is going right now. Now, why do you want that hardware accurate digital twin? Remember I was talking about it's got to be first pass success? Remember that? Test and fabricate, test and evaluate before you fabricate. In the commercial world, you have to offer a warranty on your product. You also have to make sure it avoids product liability. The only way to do that is that you not only direct test, you get to all the corner cases. And that's how they use our custom supercomputers, Palladium, Protium, and now Millennium, to get to all these spots right there. And that's how you avoid finding expensive hardware mistakes and also finding software errors after you built the stuff. We have talked to program offices that say, we need your help. We're finding 20% of our software errors in flight tests. Now, I grew up next to Edwards Air Force Base, and I know how brave our test pilots are. But even they, it's a bit of a white knuckle moment when they get in the airplane saying, are you saying there's a 20% chance I might find something up while I'm flying? And that's how you do it. And the companies that use these capabilities do this on an annual cycle. So my point about telling you this is it's something you don't need to learn and assess and evaluate. It's something you need to implement and learn. And that's been our latest mantra. Don't assess, evaluate, and assess. The companies in the U.S. that drive 60% of our GDP use it. Case closed. They're good. Learn, implement, and learn how to use it. Because once you do that, that's how you get this rapid software development. If you ever wonder, if you go down to our booth, which is right around the corner, you're going to see this little core called Tensilica. You're going to see a representation of a LiDAR unit that's on today's cars. Inside that LiDAR unit happens to be what's called a reprogrammable digital signal processor. It learns. It can learn on the fly. You can write different type of software because we have hardware accurate digital twin, and you can quickly reprogram it and get it out there to say, look for this type of an object. This is how the commercial industry writes software. This is why you don't have, when it comes together, what you see in today's defense acquisition world, when the hardware is finally out there, and even though the software guys have been writing software against the hardware, you don't see the, what's wrong here? It's because it's all verified at the same time. So what has the DoD done? Well, they actually put in the investment in there. This is a facility that's right at Cadence Air Force Base, the rapid execution of microelectronics digital engineering. It's secure cloud-based access to it. And it does support Joint Strike Fighter and a variety of other Department of Defense programs. Now, remember I said when we started doing this 6 years ago, we talked about semiconductors. Well, we actually have physics-based hardware accurate digital twinning for other type of systems too. We do data centers. Now, why is that important? Well, most of us are seeing this AI revolution, and data centers are being built all over the place. Data centers, especially the financial data centers, can't go down. Data centers, such as these data centers in the back of this satellite truck for military operations, can't go down. So our tools, our physics-based tools, will work with the data center, will help the data center designers to actually know how much power they need to keep it cool, how to get 100% utilization, and how to structure the inside of that data center to ensure you get 100% that is working 100% of the time. And I said the proof in the pudding is that the financial communities use this. The other, and it's another tool that we have is called Reality Value DC. And again, I love this tool right here because this capability because it literally is the combination of math, science, and engineering. You know, the engineers designed a tool that takes the latest physics and mathematics to say we know exactly how this is going to work. And as I said, it's a bit of an industry standard now. We do have something. In fact, this is at the Wright-Patterson Air Force Base Facility, the Millenniums, and it's hardware, software. What does it do when it does that now? The other thing we're looking at is that because these hardware uses GPUs rather than CPUs, you can solve the Navier-Stokes equations at much greater boundary conditions. And now we're looking at using our computational fluid dynamics codes not only for steady state flight, but for takeoff and landing, hypersonics, and everything else. And it's really quite something to see. In fact, this shows you it's some of the issues that we're looking at. And you're going, okay, we're finally looking at turbulence. And we actually have we now have the design tools that can actually address this and make accurately say this is how this is going to work under these type of conditions. And the funny thing about CFD, it's just not restricted to aerospace. It turns out some of our biggest customers are in fact the auto industry. You see this in here. So what are some neat things you can now do because you have these type of expanded fields? Well, for those of you who are actually worried about when you're designing a new engine, how's it going to be working? What's going to be coming out there? You've got that point right there. You look at combustors, you look at heat transfer. This is actually, you could put weapon stores on there and actually simulate it rather than having to go out to flight test. It's all reducing the flight test time to get it actually fielding the system. And it's not restricted to just airplanes. We, helicopter guys, absolutely love it. And there's a good reason why. I mean, I love these guys who fly helicopters, and you talk about incredibly brave people, but this is what we're doing. This is how they're using it right now. Say, what can we do to shift left the flight test to make sure that any modification we do to that helicopter is going to be safe and do what we're supposed to do. Even right now, we talked about this condition now, about how we're actually looking at these angles of attack, something that wasn't previously able to do until we came up with the Millennium system using the Charles software. Now, the other thing that we actually do now is that we actually have a company that is called Beta CAE. What's really neat about this, and you see these customers, why are these customers down here? These are mechanical systems. Think about this. When I was working in the auto industry, you had to build at least 5 vehicles to crash test to have enough data to say this will pass crash test standards. Companies like this now use this, and they don't have to build physical prototypes to show it meets crash test standards. That's how much the math and science and understanding mechanical of material science has progressed. And these are the customers that use it. So I think that's pretty much a compelling case about shifting left, looking right, and reducing the test and evaluation time it takes to get something out to market. So when you combine everything, this is kind of what we do now. Remember how I said we started here at chips, and you see where we are at this point right there. So a lot of people are going to be taking. I'll gladly give you a copy of this presentation if it's available to you if you ask. So the other thing is now is that, well, there are still going to be naysayers, only because people won't believe it. And we happy to we do have to do quite a bit of training in the Department of Defense. And, there's that saying we do a lot of things because we've seen a lot of things. Well, we've heard a lot of things. And we've busted every single one of these myths right here. So this is a chart that we know has made its rounds in the Pentagon, God knows how many times. It's made its round on Capitol Hill, God knows how many times, because people cast the question, well, you can't, I'm special, stuff like that. Well, you might be special, but guess what? You can still do it. And we have Cadence people around the world that are really busting these myths on a daily basis. So to conclude, this is what state-of-the-practice digital engineering brings to the Department of Defense and the Ministry of Defense. It's maintaining the warfighter edge, the speed of relevance. You do it right the first time. You've got a near 100% readiness rate. You eliminate having obsolete systems that you can't buy parts for anymore. You have to kind of scrounge to make it work. And best of all, you've got instant interoperability when you deploy when the system goes operational. You using commercial best practices such that you prevent expensive hardware mistakes. You don't have to live with mistakes anymore. You do it right the first time, and you don't have hardware software issues. In fact, that's one of the things that we hear about a lot in the field. It's like, well, that's just a software thing. Oh, that's just a hardware thing. No, in the commercial, it's a system thing. You take care of it all at once. You just don't address one side, you address both. And of course, interoperability. And that all gets down to cost savings. At the end of the day, I showed you that chart about how we're keeping these systems for 50 or 100 years. You want them to be, you want shorter, more agile upgrades. You don't want to be designing Google Chromebooks. You want to have something that can be modernized at the speed of relevance. You collect that data such that you always have the design data. If you do have to do a redesign, you can say, I like this part of the design. Let's keep this part, let's just focus here, and you get much shorter design cycles. At the end of the day, the governments actually control their own destiny in terms of supply chain management. So with that, that's all I have. I'm glad to try to address any questions you may have at this point, or you can always visit us at our booth, which is around the corner. Thank you very much. Any questions? I must be getting really good at this.